Hello, this is an example problem for lesson 3, how to use the ANSI fit tables. Okay, so this is just like problem 2 of your assignment 3. You got 3 of these things that you have to calculate. The problem statement is, calculate the hole basis limit dimensions for the pin and hole shown. The nominal size is 0.4375, that's 7/16 of an inch, and the fit is running and sliding RC5. Okay, first of all, the pin and hole shown kind of looks like this. And what we are to do is to come up with these limit dimensions by using the specified fit. The specified fit here is RC5. Now how you do that is you go to the fit tables that I give you in the materials folder, and that fit table looks like this. Okay, so there's different classes of fits. A running and sliding fit means you always have clearance between the parts, and then there's different fits that go in here, RC1 up through RC9. The hatched here bar represents the size and the tolerance of the hole. Okay, and then this black bar here represents the size and the tolerance of the shaft. So these are running and clearance fits. So therefore this gap here from the dark bar to the hashed bar, that's actually the magnitude of the clearance at that fit. So if you go to RC8, there's a little bit less clearance, RC7 is a little bit less clearance, etc., etc. Now these are all clearance fits. Running and sliding means the parts move together relative to each other. So those are the fits. So what happens is somebody worked out a long time ago that for each of these fits, okay, here's RC1, RC2, RC3, RC4, and then here are the different nominal sizes, okay? So really what you try to do is you try to look up your nominal size in your class of fits, which is the first thing that you have to do for this example. Before I move on, I want to talk about these other things. This is a locational clearance fit. Again, these are all clearance fits in here, and then LC1 through LC11, and then by the time you get up to this one, the LC11, it's a pretty loose fit. And it's used just to locate parts when you're putting parts together. Now if we've talked about transition fits, this is LT, that's a transition fit. Some of them are clearance and some of them are interference. You can see these bars, the hatches and the dark bars kind of overlap each other. That means the shaft is always bigger than the hole. And then same here, these are these force fits over here, FN1 through FN2. Again, these are force fits. You have to force that pin into the hole because, as you can see here, this would be the smallest hole right here, and man, that thing's just it's gonna be hard to put in. So anyways, this is the charts that decide what those clearances are. Now if the parts are bigger, then probably they need more clearance to get the same. So somebody's worked all of this out. So we have shafts and hole sizes from 0.12 all the way up to 15, 19, and 20 inches. Okay, so you're talking about from little pins and parts to all the way to wheels and hubs on railroad wheels. Let's go back to our example. So our example says, calculate the hole basis limit dimensions for the pin and hole shown. The nominal size is 7/16 of an inch, and the fit is an RC5. Okay, so I showed you where to find the tables. Locate the table for RC5. Okay, and how you would do that, you'd come over here, RC1, RC4, that would be on the next page, it would be RC5. Then 0.4375. That means we want to look right here in this part of the table. 0.4375. Here's where we want to look in this part of the table. RC5, 0.4 to 0.7. Okay, this is the nominal size range that we are in. And then here are the dimensions, 1.2, 2.9, 1.0, and 0. If you notice, everything on this table is whole basis. How can you tell it's whole basis? Because the minimum whole here is 0. Minimum whole 0. Minimum whole 0. Okay, that's how you know that this is a whole basis. We're not even going to do shaft basis in this class. We're just going to use this one as an example for how to do the whole basis. Let's go back to our problem. So these are the numbers that I highlighted from the other table. Okay, locate the row that is applicable for the nominal size, and we just did that. So here is our applicable fit data for our problem. Okay, there are 3 columns applicable for this fit. First of all, the clearance, right here. And the numbers in this column represent the clearance range between the shaft and the hole. So this is clearance. These are clearance numbers. If we take the hole and subtract from it the shaft, we're always going to end up with positive numbers because this is a clearance fit. Okay, so now the 1.2 represents the minimum clearance between the hole and the shaft, and that's going to be 0.0012. Okay, so when we see 1.2, we assume that the decimal place, this decimal place here is 3 places over. Okay, so that means our clearance on our fits between these two parts is going to be 0.0012 to 0.0029. Now, the hole limits. These two are the hole limits. The plus 0.9 represents the largest hole. That would be 9/10 larger than the nominal. Okay, so the maximum hole size is the minimum hole, which is the 0.4375, plus the 9/10 of a thousandth, and I get 0.4384. Now 0, okay, again, we're using the whole basis, so this is going to be 0, represents the smallest hole. So our smallest hole is 0.4375. Okay, next we look at the shaft tolerances here. Okay, so negative 1.2 represents the largest shaft, and so we're going to deviate from the nominal size of 0.4375 by 0.0012. So if we take 0.4375 and we subtract from that 0.0012, we got 0.4363. Okay, that is the largest shaft size. Okay, we do the same thing for minus 1.9 and we get the smallest shaft size. Okay, so therefore, here's what our answer is. Okay, the whole size limits of the tolerance are 0.4384, we calculated that up here, to 0.4375. Notice how I'm putting the larger number above the smaller number because I'm using limit dimensions. Okay, and then the shaft is a maximum of 0.4363 here, and it's a minimum of 0.4356 here. Okay, so how do we know we did this right? How do we know we did this right? The solution can be easily checked for correctness. I encourage you to do this. If we were to take the min hole and minus from that the maximum shaft, we get 1.2 thousandths, 0.0012, which matches our 1.2 here. Now, if we were to take the max hole and subtract from it the min shaft, we got 0.0029, which again is our minimum clearance, which is stated right here. So this is how to use the charts to do the homework assignment in problem number 2 of assignment 3. Thank you.